Hello to everyone. Welcome to the course on numerical linear algebra and application. In continuation to the previous lecture, we are going to give some applications, and this lecture is 60th lecture of 12th module. You see, there are many more applications as already we have seen in the previous 3-4 lectures. In continuation to that, I wanted to give you a versatile applications where quite often we do come across in day-to-day life. In the applications of science and engineering, biological systems, medical applications, agriculture, weather prediction, and food processing industries, and so many applications. The first and foremost application which I wanted to present here is computer graphics. All of you knowing very well, computer graphics play a vital role in the design of chips, in the design of bearing mechanisms for vehicles, in the design of manufacturing units, in the design of chips, etc. The images are moved around, their scale is changed. So the scaling of the images is not uniform. It depends upon, for example, if you take the example of a groove bearings, how the groove is fitted, accordingly the shape gets changes. Then 3 dimensions are projected on 2 dimensions. That's also one of the things which we will do in the image processing and noise removal and so on and so forth. All the main operators are done by matrices. You know, all the elements are actually managed via reflection, scaling, refraction, and so on and so forth by using matrices. The transformation of 3-dimensional space are done with 4x(n) matrices cannot, because you would expect a 3x3. The reason for the change is that one of the 4 key operations cannot be done with a 3x3 matrix operations. As we see that, the reason is that one of the 4 key operations cannot be done with a 3x3 matrix multiplication. The foremost one is what we call translation. That is, shift the origin to another point P0, that is x0, y0, z0. That means x coordinate value is x0, y coordinate value is y0, z coordinate value is z0. So that means x, y, z will be mapped to x0, y0, z0. Then second one is what we call scaling. Scaling in all directions by a factor of C1 factor, C2 factor, C3 factor. So that means essentially you will have C1 factor, C2 factor, C3 factors. By scaling. Then rotation around an axis through the origin or an axis through P0, point P0. Translation is the easiest. Just add x0, y0, z0 to every point, but this is not linear. No 3x3 matrix can make the origin. So we need to have some translation. So we need to have the coordinate system, that is 0, 0, 0, 1. That is why the matrices are 4 by 4. Actually, we are handling 3 by 3, but ultimately, when you wanted to do it practically, it turns out to be 4 by 4. The homogeneous coordinates of the point x, y, z, that is the point x, y, z, or x, y, z, 1. And we now show, now they do work over here. And when you talk about the translation, shift the whole three-dimensional space along the vector v0. This is the vector v0. The origin moves, that is x0, y0, z0. The vector v0 is added to every point v in R3. Using homogeneous coordinates, the 4 by 4 matrix T shifts the whole space by v0. So, you translation of this matrix, that is matrix T, that is 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, x0, y0, z0, 1. Remark is, computer graphics work with row vectors. We have row times matrix instead of matrix times the column. One can quickly check that 0, 0, 0, 0, 1 transpose is nothing but the x0, y0, z0, comma 1. To move the points x0, y0, z0, 0, 0, 0 to xyz by v0, change to homogeneous coordinates 0, 0, 0, 0, 1 and xyz to 1, then multiply by t. A row vector t times gives a row vector, that is the vector moves to v plus v0. So, that is x, y, z, 1 transpose, that will be equivalent to x plus x0, y plus y0, z plus z0, comma 1. The output tells where any v will move. It goes to v plus v0. Translation is now achieved by a matrix which are impossible in R3. So, in fact, we were trying to do it translation in R3, so which is not possible in R3 coordinate system, and we wanted to have the 4 dimensions. That is what we do it in the translation case. And scaling is, to make a picture fit a page, we change it with its width and height. To make a picture fit a page, we change with width and height. A copper will rescale a figure by 90%. In linear algebra, we multiply with 0.9 times the identity matrix. That matrix is normally 2 by 2 for a plane and 3 by 3 for a solid. You see, when you talk about the that is for a plane, right? For a plane case, it is 2 over 2, and for solid case, you take it as a 3 over 3. For it is a plane case, it is 2 by 2, and solid case, it is 3 by 3. In computer graphics with homogeneous coordinates, the matrix is one size larger. So, rescale the plane, you get like this 0.9, 0.91, and this is the 0, 0, and this is the 0, and this is all zeros. So, it is in the plane. So, it is in the solid. What happens? You see the constant times, and last one is 1, zeros, 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 zeros. So, it has become what you call a diagonal matrix. Of course, this is also a diagonal matrix. This is also a diagonal matrix. Rotation is a rotation around an angle theta at the point that is 0, 0 is a transformation that maps every point t in the plane to the point t prime. That means t to t prime. That is OT is equal to, absolute value of OT is equal to OT prime, and angle of TOT prime is equal to theta. By conversion, a rotation by the positive angle theta goes counterclockwise, while rotation by the negative angle theta goes clockwise. So that means essentially you will have x is equal to r cos phi, y is equal to, you will have r sin phi. X is equal to r cos phi, y is equal to r sin phi. So where this phi, where phi is located from the horizontal x coordinates, horizontal x coordinates. Horizontal x coordinates with a distance r from the origin of the coordinate system leads to a new point, that is t prime. So t prime is equal to t prime of x prime y prime. Similarly, coordinate of the new point, that is t prime of x prime y prime, can be expressed as x prime is equal to r times of cos of theta plus phi, and y prime is equal to r of sin theta plus phi. So x prime is r cos phi cos theta minus r times of sin theta sin phi, expanding this. Similarly, this is that which can be written as x. So this is x equal to r cos theta, that is x cos theta minus y sin theta. This x prime becomes, similarly this y prime is r cos phi sin theta plus r sin phi cos theta. So which will become like this. So essentially which can be written as this x prime y prime. The matrix is nothing but, that is cos theta minus sin theta, and it is sin theta, and it is cos theta multiplied with x, y. So similarly, when you talk about the reflection, reflection is a special case of a scaling where the size of the objects does not change. For the scaling factors, Sx is equal to minus 1 and Sy is equal to 1, and Sx is equal to 1, S of y is equal to minus 1. There is a reflection is about the x and y axis. Then shear is skewing the objects with respect to the x or y axis is called the shear transformation. Skewing by angle alpha with respect to the x axis by an angle beta with respect to the y axis. So you will have this form, that is x prime is equal to x plus y times of tan of beta, y prime is equal to y plus x times of tan of alpha. In the matrix form, so which can be written as x prime y prime is nothing but 1 comma tan of alpha, and it is tan of alpha comma 1 multiplied with x and y. So when you talk about the homogeneous coordinate system, the process of implementing several successive transformations is by using the Cartesian coordinates. Computationally more extensive, namely it can be noticed that to perform translation, matrix addition is carried out, while the performing other transformations only matrix multiplication is carried out. In order to reduce them to matrix multiplication, homogeneous coordinates are introduced. Thus, each Cartesian point T of x, y, that is T of x comma y, is converted to a homogeneous coordinate system, that is T of x, y, z. And a coordinate system with this point representation is called a homogeneous coordinate system. Although triples of coordinates commonly display a point in space, here they represent a point in the plane or a 2D point. Two sets of homogeneous coordinates, that is x, y, z, to x prime, y prime, z prime, represent the same point if one is a multiple of the other. For example, coordinates 1, 2, 3. So, if you have a coordinates 1, 2, 3 and 2, 4, 6 represents the same point, it can be concluded that one point is homogeneous coordinates can be displayed in infinitely many ways. That is, one whole class of triples of coordinates represents with one of the point, that is T of x, T of y, T of w, where T is not equal to 0, actually represents a line in 3D space. It should be noted that at least one homogeneous coordinates must be different from 0, meaning that the point 0, 0, 0 is not allowed. If the coordinates w is not equal to 0, each of them can be divided by w. That is why the point can be written as T of x, y, w, that is equal to T of x by w, y by w, comma 1. So, which will be equivalent to x w, y w 1. All such points from a plane with equation w is equal to 1 in 3D space, that is, if w happens to be 0, then actually it is a point of infinity. So, that case is avoided, which is not considered as in more detail. So, if w is equal to 0, then the denominator is 0, so its numerator will blow up whole fraction. So, therefore, that would be beyond the scope of this discussion. The usage of homogeneous translation matrix becomes, that is, m of TR is equal to 1, 0, Tx, 0, 1, T of y, 0, 0, 1, where translation is reduced to a matrix multiplication. So, you will have 1, 0, Tx, 0, 1, Ty, 0, 0, 1. So, 1, 0, Tx, 0, 1, Ty, 0, 0, 1. Where translation is reduced to a matrix multiplication. So, ultimately, we would be able to write into this form. Furthermore, the homogeneous translation matrix, which we call it as, that is 1, 1 element, 1, 2, 1, 3. Similarly, this second row, similarly this third row. So, which I called as the M translation matrix. Homogeneous rotation matrix. That is, when you talk about the M rotation, cos of phi minus sin of phi 0. This is sine of phi, cos of phi, 0, 0, 0, 1. So this is what is called M rotation, and this is called M translation. So this is the translation. And this is called rotation. This is called rotation. This homogeneous scaling matrix, when you talk about the scaling matrix, that is capital M of scaling, which will be Sx 0, 0, 0, Sy 0, 0, 0, 1. And M shearing is 1 tan of beta, 0 tan of alpha, 1, 0, 0, 0, 1. This is the A11, this is the A12, this is the A13, and this is A21, and this is A22, and this is A23. This is A31, and this is A32, and this is A33. In order to conduct several sequences of the transforms, so you will have T prime, that is equal to M translation, M rotation, M scaling multiplied with T. That is scaling and also the shearing. So in order to conduct several sequences of the transformation, all these transformations must be compounded. After the implementation of all transformations, for example, scaling, rotation and translation over the point T in this original order, and the coordinates of the point T prime could be calculated in the following way. So T prime is nothing but M translation, M rotation, M scaling times of T. And the coordinates of point T prime could be calculated in the following way. So T prime is the new updated coordinate system after having done the translation, rotation and scaling. That is, they could be calculated by multiplying the homogeneous scaling matrix, homogeneous rotation matrix and homogeneous translation matrix respectively in a single matrix ideas. So these are the some of the applications where we could see in the computer graphics. In continuation to that, there is a called matrix computer graphics. There is a very specialized name called matrix computer graphics. In the elementary level, matrix calculation is an integral and significant part of the mathematics curriculum for students, as you know very well. One of the possible ways of matrix operation implementation is computer graphics. So computer graphics, what we do? So we do have a lines, we do have a polygons, we do have a circles, you do have a trapeziums, we do have a rectangle, we do have a diamond shape, rhombus, right? You do have a brick shape, eight nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 nodes. Here how many nodes? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And a triangle, if you look at triangle, 1, 2, 3 shapes. This is the master node. So, linear operators and their basic properties. Basic definitions, operations with operators. Let x comma y be linear spaces. We say that pi is a map from x to y. For any x belongs to capital X, there exists a unit vector pi x belongs to capital Y. We also say in this case that the function phi with values in the space y is defined on the space x, and we write x is approaches to phi of x. We note that at the same time, not every vector y should be the result of the mapping phi of some vector x belongs to capital X. Some vector small x belongs to capital X. So, we say that the map phi is a linear map for every x comma y belongs to capital X and a scalar alpha beta such that phi times of alpha x plus beta y will be equivalent to alpha times of phi of x plus beta times of phi of y. In linear algebra, almost all mappings are linear and they are called linear operators, or in some context operators. Usually operators are denoted by capital letters. For example, relationships 1 for a linear operator A will be written as, so A times of alpha x plus beta y is equal to alpha times of ax plus beta times of ay. So, using the definition of a linear mapping, and we say that A naught is equal to 0 and A is the operator over here. So, that means the values of alpha and beta. So, alpha, beta are the scalars. For these scalars, so I will have a mapping A times of alpha x plus beta y will be equivalent to alpha times of A of x plus beta times of A of y. So, that means essentially it preserves the linearity, right? It preserves the linearity. So, if an operator maps a space x into a space x, then we say that it acts a transformation of the space x. If some basis, that is E of j, j is equal to 1 to n, is fixed in finite dimensional vector space x, to define a linear operator A on x, it is enough to describe the action of this operator all basis vectors. So, because x is equal to summation j is equal to 1 to n psi of j E of j, then we will have A of x will be equivalent to summation j is equal to 1 to n sigma j a e j. Operations with operators. So you will have an operations over that you are giving another operator. We define the linear combination of two operators, that is A is mapped to xy and B is mapped to xy. So the mapping which we call it as alpha times of A plus beta times of beta will be, that is x mapped to capital Y. So we will get this as alpha times of A plus beta times of Bx is nothing but alpha, you take it outside. So you will have essentially alpha times of Ax plus beta times of Bx for all x belongs to capital X. Where alpha, beta are scalars, we define the product of two operators, that is A is mapped to x to y and B is mapped to y to z. Then the mapping, that is B of A, that is x to z, is given by, that is B of Ax will be equivalent to B times of A of x for all x belongs to capital X. The reader can easily prove that alpha A times of beta B and beta B are linear operators. The product of a finite number of operators is defined in the same way. The reader will have no difficulty in showing that if the product of operators, that is C, B, A are defined, then you will have what you call C times of BA is equal to C times of BA, which is equal to CB times of A. So there are many more examples to see this kind of operators. Examples of linear operators. If you see the linear operators, the null operator. So all of you knowing very well, null operator maps x to y is defined as null of x acting on x is equal to 0 for all x belongs to capital X. This operator transforms every vector of the x into the 0 vector of the space y. So that means x is mapped to capital Y. The identity operator, another operator which is known very well, x to x defined by I of x is equal to x for all x belongs to capital X. This operator transforms every vector of the space x into itself. The projection of the operator, that is the linear operator x, be a direct sum of the succession of L and M. So that means if you have x, so you will have x1 plus x2. So x1 belongs to L, x2 belongs to capital M. And P is the operator, and this operator actually mapping to the vector x to a operator called L. So essentially you will have the 0 operator, you will have the identity operator, and you will have the projection operator. So in what happens is, the operator P is what we call the projection operator onto the subspace L in parallel with the subspace capital M. If X is an inner product space and can be represented as an orthogonal sum of the subspaces L and M, then the operator P is called the operator of the orthogonal projection. So this is what is called orthogonal projection. Orthogonal projection. Let us prove that the operator P is linear and you will have x is equal to P into x plus x into 2, and y you call it as P into y plus y of 2, and this xy is belongs to capital X, x2 y2 belongs to capital M. Then for any scalars alpha and beta, so you will have alpha x plus beta y will be equivalent to alpha times of p of x plus beta times of p of y, alpha x2 plus beta of y2. So, well and one are the subspaces. You get into this kind of equations. So, in the same manner, we can introduce the linear operator Q. The projects Q is the linear operator that projects the space x onto the space capital M. That means x is projected to capital M. The operator is what is called Q. We can easily get the following equalities, that is P plus Q will be equivalent to 1 and P multiplied with Q is equal to 0. Also, you will have P square is equal to P and Q square is equal to Q. So, generally if the space X is a direct sum of several subspaces, then you will have X is equal to L1 into 0, L2 into 0 and so on and so forth, and P is the projection operator onto the subspace Li. So, you will have the P1 plus P2 plus etc. P of k is equal to I, and P square of I is equal to Pi, and Pi P of j is equal to 0 for all I is equal to j. So, the matrix vector multiplication is also in the similar fashion. If you have A and comma n be a rectangular matrix, we define the map A, that is set of all complex plane n to set of all complex plane m such that y is equal to A times of x. The matrix vector multiplication is the linear operation. So, therefore, the operator that is A is mapping to C of n to C of m is linear, So, the inverse operator is, that is a linear operator, that is A of, that is x to y is called the invertible if there exists a map that is beta of y to x such that beta of ax is equal to x for all x belongs to capital X. That is a beta of y is equal to y for all y belongs to capital Y. So, that means this beta tends to y to x satisfies is called an inverse map. Now, let us check that if an inverse beta of the map A exists, then B is a linear operator. Then the B is called a linear operator. Let this y1 comma y2 it belongs to capital Y and alpha comma beta belongs to capital C. Then we take x1 is equal to beta y1 and x2 is equal to beta y2. Then you will have this ax1 will be equivalent to a beta y1 is equal to y1. So, therefore, beta times of alpha y1 plus beta times of y2 is nothing but, that is beta times of alpha into ax1 plus beta into ax2. So, this is the equation which we got it. That is alpha x1 plus beta x2, that is equal to alpha times of beta of y1 plus beta of y2. So, we claim that if a linear operator, that is a x to y is invertible, then this operator is a bijective map acting from the x space to space y. So, you will have, that is ax1 is equal to ax2 and beta of ax1 is equal to beta of ax2. Hence, x1 is equal to x2. So, therefore, the mapping is with some vector x belongs to x. So, it is easy to see that if a linear operator A is invertible, then it is a unique inverse. It is easy to see that if a linear operator A is invertible, then it has a unique inverse. The inverse operator to the operator A is denoted by, that is A inverse. So, you will have A inverse exists, then you will have A inverse whole inverse is equal to A. So, the examples are the identity operator is invertible. So, you will have I inverse is equal to I. Obviously, the null operator is the non-invertible operator. So, that is L not equal to X. Then the projection operator, that is projection operator P is X to L, is the non-invertible operator. So, you cannot able to invert it, non-invertible operator for this matrix. So, the third one is any square matrix A of order n defines the linear operator acting in the space, that is C of n. If the matrix A is non-singular, then this operator is invertible. So, you will have the A is mapped to X to Y and B is mapped to Y to Z. Be invertible operators, the reader can check easily that is B of A whole inverse is nothing but A inverse times of B inverse. The coordinate representation operator is let xn be a n-dimensional operator in space and En is equal to, that is Ek, k is equal to 1 to n be a basis for x. So, you will refine this C of n as into x of n. By the rule, you can have this matrix. So, x is equal to E of n times of xi and xi is equal to C of n. Evidently, this operator is linear and we defined by E. So, if x belongs to the x of n, then there exists a unique representation, that is x is equal to summation k is equal to 1 to n xi of k E of k, because E of n is the basis. So, the scalars xi of k, that is k is equal to 1, 2, etc. n are the coordinates. So, you will have x to xi where chi is equal to En of xi. Using the definition of the operator E and E inverse, so that is you will get E inverse times of E of xi is equal to xi for all xi belongs to C of n, that is E times of E prime of x is equal to x for all x belongs to xln. Usually, to calculate the coordinate representation of x, it is necessary to solve a system of linear algebraic equations with a square non-triangular matrix x. If xn is inner product space and En is a orthonormal basis, then the coordinate representation of x can be calculated more easily. So, therefore, from this lecture what we learned is what are the applications available in computer graphics, and you do get the matrices, how the matrix represents the each elements in different shapes by scaling, by translation, by sharing, and these properties. So, the mapping changes and also the shape also will get changes in the computer graphics. So, this is one of the basic applications of the matrices in computer graphics. So, we will learn a few more examples in the next lecture. Thank you very much for being with me. Thank you once again.